Hello everyone, we're Carson, Marvin, Michael, and Omer, and we're going to be talking about our solutions for the Michoko case study. We're faced with the following problem. The EPA has new regulations set in mind for emissions, and we are faced with four choices designed by our marketing and engineering teams in order to fix these problems. Our first option would be to adapt our production levels to conform with the new EPA regulations. We would accomplish this through adjusting our product mix based on a linear programming approach. Our second option would be to install housings to capture harmful particulates. This would incur a small capital cost, followed by additional annual costs. Our third option would be to buy new production equipment in order to reduce emissions. This would incur a large capital cost, but no additional annual costs. Our final option would be to lobby against the enactment of these regulations. This would require us to spend a relatively small amount of capital in order to potentially thwart the advances made by the EPA. In the following slides, my colleagues will talk about the analysis of these strategies and our recommendation based on this analysis.
Let's have a look at our linear programming formulation. Our decision variables would be xpt should be larger than 0, the red circled, which says how much of product type P in time period T do we produce. And in the case of question B, we would have a binary variable y housing per time period T, which says whether we would buy or buy not the housing equipment and start that. Let's have a look at the maximization. So we want to maximize our revenue, and it's clearly important if we look at the red circled parts that we will get the sum of each period from period 1 to period 5, and whatever we earn in that period will be multiplied by our NPV factor. Then it is important to look at the blue part, which essentially says that we take the revenue per product minus the cost per product and multiply it by the amount of products we have sold in that period. The other parts would be the orange one saying if we buy the housing option in this period, we will have to encounter the fixed costs. And the green option says if we have bought the housing option in this period or any period before from 1 to the current period T, then we would have to pay the variable costs in this period. If you sum that all up, multiplied by the net present value, and then this is what we want to maximize. For our optimization, we have many constraints. The most important one is that our production in the red part X cannot exceed our demand, and this cannot happen for any product nor for any time. The green box, which is the next constraint, tells us that our production times the rate for all of the products we produce in that time period, the sum of them must be smaller than the maximum capacity, which makes sense because we cannot produce more than our capacity. And the next one says, if we look at the blue box, that whatever we produce multiplied by the emissions we have to incur due to that production, and the sum of that must be smaller than, on the right side, the emission capacity, which changes over the time. And then we have an interesting part on the right side. So we have this sum from I equals 1 to T of Y housing, which will give us whether in this time period we have or have not installed the housing yet. So if we haven't installed the housing yet, this multiplication will be 0, and we have to make sure we are in the emission capacity. If we have already installed that, we will have big M on this side as an addition, and this big M will be a large number, like a very, very large number, saying for whatever we produce, we will never be able to get as much emissions as this large M, and it simply says if we buy housing, we don't have to care about the emissions capacity problem. And the last constraint will simply say that our Y housing can only be one for once in a time, so we can only once upgrade our facilities.
A common approach to make restrictions on emissions that are imposed by the government more efficient is to implement the option to trade emission rights. Companies that emit less than they are allowed can sell their excess emission rights, and other companies can buy them in order to increase their emission levels without having to pay financial penalties. Since these emission rights usually don't have a fixed price, it is important for our company to know how much the right to emit one additional unit is worth. Therefore, we adapted our linear programming model. We relaxed the emission constraints for each year and calculated the new objective function. By deducting the value of our basis alternative from those new objective values, we obtained our reservation prices for one additional unit each year. 1 unit equals 1 ton in this case. The basis alternative is the alternative in which we don't invest in anything and are restricted to 80, 60, 40, and 20 tons of emissions for years 2 to 5 respectively. If you look at the table, there is a clear trend recognizable. Except for year 3, the reservation price gets higher as our constraints on emissions become more strict, since demand levels stay equal over those 5 years. Still, this solution has some limitations. We know how much one additional unit is worth, but we also know that the values we calculated are not constant. This means that we neglected our other constraints, like demand, for example. As soon as we reach the demand levels, one additional unit of emission rights is worthless. In order to make more in-depth calculations, we need to take more information and also some assumptions into account. Please read our detailed report for further analysis.
Through our analysis, we found that strategy A is suboptimal, as it is too passive and does not draw in enough profits in relation to our market demand. Strategy B is feasible, but as we collect more particulates in our housings, we might need to invest more money in waste management solutions, which might incur additional significant costs. Strategy C is also feasible, but we might have extra training costs for new equipment. Additionally, newer machines will likely have a greater salvage value at the end of 5 years, if we decide to sell them. While strategy D technically brings in the most profits, it is also considered to be very risky. An all or nothing approach in this case is not preferred. Additionally, not lobbying against the environmental regulations might promote a greener company image, which could come in handy.
In conclusion, the final decision would have to be taken based on which direction shareholders and upper management feel is best for the company. Our analysis using linear programming concluded that strategy A is too passive and returns the lowest profit due to the imposed regulations. Both strategy B and C are reasonable options with an estimated profit of roughly 6.94 million, with strategy C requiring more capital to implement. For strategy D, there is a 30% chance of failure, which will relegate sales to be almost 3.04% lower than strategy A. However, the potential benefits would be profits almost 40% higher than the average of all calculated options. Besides economical factors, there are also environmental and social concerns. Not joining the lobbying group would promote an environmentally conscious company image, which would in turn open up new opportunities for investment in the future. Also, it is not clear how long this lobbying group can sustain, since recent trends show that both society and industry policy become increasingly sensitive to environmental problems. Taking all these arguments into account, we recommend strategy C as the optimal solution. Thank you.